What is pi? Pi, represented by the Greek letter pi, is defined as the ratio of a circle's circumference to its diameter. Mathematically, pi is expressed as the circumference divided by the diameter. Pi is approximately equal to 3.14159, but its decimal representation continues infinitely without repeating. Pi is an irrational number, which means its decimal representation never ends and never repeats. It cannot be expressed as a simple fraction. Pi has been studied for thousands of years across many civilizations. Ancient mathematicians used various approximations, while modern computers can calculate pi to trillions of digits. For example, in a circle with a diameter of 2 units, the circumference would be pi times the diameter, which is approximately 6.28 units. To summarize, pi is the constant ratio of a circle's circumference to its diameter. It's an irrational number with an infinite non-repeating decimal expansion. This fascinating constant has been studied for millennia and appears throughout mathematics and nature. In geometry, pi appears most prominently in formulas involving circles. The fundamental circle measurements, circumference and area, both involve pi. To understand why the circumference equals 2 pi times radius, imagine dividing a circle into arcs. If we straighten these arcs, we get a line whose length equals the circle's circumference. For the area, we can think of a circle as composed of concentric rings. Another approach divides the circle into wedges, which can be rearranged to form a shape resembling a rectangle. The area of this rearranged shape equals pi r squared, where r is the radius. Let's see these formulas in action with an example. If a circle has radius 3 units, the circumference equals 2 pi times 3, which is 6 pi or approximately 18.85 units. And the area equals pi times radius squared, which is 9 pi or approximately 28.27 square units. Pi plays a central role in trigonometry, particularly in the unit circle and the measurement of angles. In the unit circle, angles are measured in radians, where pi radians equals 180 degrees. This makes pi the natural unit for measuring rotation. The unit circle contains all the key angles in terms of pi. One complete revolution around the circle equals 2 pi radians. In the unit circle, the x-coordinate of a point represents cosine of the angle, while the y-coordinate represents sine. As we move around the unit circle, the sine and cosine values change in a periodic pattern. One complete cycle is 2 pi radians. Both sine and cosine functions have a period of 2 pi, meaning they repeat their values every 2 pi radians. This is why pi is essential for describing oscillations and waves. The periodicity of pi makes it fundamental in describing waves and oscillations in physics and engineering. Pi appears in numerous fundamental calculus formulas and connects seemingly unrelated areas of mathematics. Pi appears in many important integrals in calculus. For example, the Gaussian integral, which is essential in probability theory, equals the square root of pi. Another example is the integral of sine x over x from 0 to infinity, which equals pi over 2. The integral form of the inverse sine function also gives us pi over 2, showing pi's connection to trigonometric functions in calculus. Pi also appears naturally in infinite series. The Basel problem solved by Euler showed that the sum of reciprocals of squares equals pi squared over 6. The Leibniz formula for pi gives us pi over 4 as an alternating series, although it converges slowly. Another beautiful formula is that 2 pi equals the integral of 1 over 1 plus x squared. Perhaps the most beautiful appearance of pi is in Euler's identity, which connects 5 fundamental constants of mathematics in one elegant equation. This equation brings together e, I, pi, 1, and 0, 5 fundamental constants from different areas of mathematics. Pi serves as a bridge connecting seemingly unrelated fields of mathematics. It appears in number theory through series expansions. In analysis, pi is central to differential equations and integral formulas. In geometry, beyond circles, pi appears in volume formulas and higher dimensional spaces. And in probability, pi emerges in the normal distribution and other statistical functions. This universality of pi across mathematical disciplines highlights its fundamental importance as a mathematical constant. Pi appears throughout the natural world in circular and spherical forms. When a drop hits water, it creates circular ripples. The propagation of these waves follows mathematical principles involving pi. Planetary orbits incorporate pi in their mathematical descriptions. Kepler's third law relates the orbital period to the semi-major axis, with pi squared in the equation. Many objects in nature form spheres, from fruits like oranges and apples to bubbles and water droplets. Spheres are the most efficient three-dimensional shape, enclosing the maximum volume for a given surface area. This efficiency is why they appear so frequently in nature. This relationship, governed by pi, minimizes the energy and materials needed to create and maintain these structures. When we compare shapes with equal volumes, spheres have the smallest surface area. This is why bubbles form spheres, and why many fruits and organisms adopt this shape. From rainbows and water droplets to soap bubbles and planetary systems, pi emerges naturally in countless circular and spherical structures throughout our world. Pi appears prominently in the normal distribution formula, also known as the bell curve. Here's the formula for the normal distribution, with pi clearly visible in the denominator. The normal distribution creates this iconic bell-shaped curve, which describes countless natural phenomena. Let's break down this formula to understand why pi is essential. Each component serves a specific purpose. Pi appears in this formula because of its connection to the total area under the curve, which must equal 1, representing 100% probability. The normal distribution describes many natural phenomena. Here are some examples that follow this pattern. Because of its presence in the normal distribution, pi plays a crucial role in data science, machine learning, and statistical inference. Through the normal distribution, pi connects mathematics to our understanding of natural variability and random processes. The universality of pi extends far beyond our Earth, reaching into the cosmos itself. Pi is a universal constant that would be recognized by any advanced civilization in the universe. No matter what symbols or language an alien civilization might use, they would discover that the ratio of a circle's circumference to its diameter equals pi. Mathematical Platonism suggests that mathematical truths like pi exist independently of human minds. We discover these truths rather than invent them. Pi has been calculated to increasingly precise degrees throughout history. As of 2022, we've calculated pi to a staggering 100 trillion digits. Despite calculating pi to trillions of digits, mathematicians continue searching for patterns or structure in this seemingly random sequence of numbers. Pi represents more than just a mathematical constant. It's a universal truth that transcends human culture, language, and even the boundaries of Earth itself. This universality is part of what makes pi so fascinating to mathematicians and thinkers throughout history.